Um, hey everybody, Smitty Halibut here, Mark Smith, working on the next iteration of the badge, of the DefCon DarkNet badge that I've been spending a couple of episodes on. Last time I was doing mostly just the hardware that it takes to recreate the badge-specific bits of it. So like the infrared transmitter and receiver. I did some power, not a lot though. I've definitely got some more to do there. Put the display on the schematic, the buttons, the LEDs on the back, that kind of stuff. I did the things that made it a badge, but what I'm still lacking is a lot of the support hardware that this year we just bought this STM32 module that had the STM32 on it, but it also had both of the crystal oscillators and a reset button and a bunch of capacitors that are on the bottom side of this board that you can't see. A bunch of other support hardware that that I need to be able to recreate. A bunch of power supply bypass caps, so some capacitors kept right close to the power supply leads on the chip. And the crystal oscillators. There's an 8 megahertz oscillator that's used for the main system clock, and then there's also a 32 kilohertz oscillator that is used for a real-time clock that is built into the chip. And all of those are pins that are on the CPU that we need to break out and put those connectors onto. So, yeah, that's what we're going to be doing today. Doing a lot of the support hardware that's needed for the microprocessor. So I did a lot of kind of pre-work setting up some documentation here. Right here is the pinout of the microcontroller that we're using. This is the STM32 F103, same one that we've been using. This is what I used for outlining the component in KiCad. And I labeled all the pins like PA1, PA2, but I did not label them with their functions. So like PC13 is a tamper evident pin, which I don't think we're going to be using, but PC14 is the 32 kilohertz oscillator pin. PC15 is the other 32 kilohertz oscillator. PD0 is the oscillator, the 8 megahertz oscillator, and PD1 is the 8 megahertz oscillator out. So you just hook the two pins of the oscillators out to those. So that's something that I'm going to need to. I'm not going to update the components to have those labeled, although one could make a pretty strong argument that I should, but I'm not going to because I'm lazy. But what I am going to do is I'm going to go in and use, PC14, PC15, D0, and D1 and hook them up to the oscillators, plus a few other supporting capacitors and whatnot. The other thing that we're going to be doing is a lot of the power supply leads in the microcontroller need some bypass capacitors. These are just capacitors that you put next to the pins on the CPU. And when the CPU needs to do a burst of energy, when it needs a burst of energy, it pulls it from these capacitors. And these capacitors keep the power supply line from going down. And it keeps a lot of noise off of the power supply lines. There's probably some other thing that bypass caps do that is, a proper engineer would know, but I don't. I just think of them that way as providing little local power stores. But you do need to have, 100 nanofarads, which is what it says right here. 100 nanofarad capacitors, which is what, a 0.1 microfarad. So we need to put some 0.1 microfarad capacitors next to all the pins. Now this is saying 5 times 100 nanofarads because that's for one of the bigger packages. We only have VDD 1, 2, and 3. And possibly a 4. I think it's only just 1, 2, and 3. So we're only going to have 3 of them. Although it does say that we need to have one 4.7 microfarad capacitor on the VDD pins. And then for the analog reference, the VDD-A, which is analog, the analog supply, it also wants a 0.01 microfarad, which is a smaller capacitor. And you think, well, gee, why would you want a smaller capacitor there? Shouldn't a bigger one be able to do the same kind of filtering? And the answer is kind of. Yes, on bulk scales, but the smaller the capacitor in this case, the quicker it responds. The larger capacitors, one of the problems that they have is they don't respond super quickly to they don't respond super quickly to immediate transients. And so, like when you really want to have a clean power supply line, one thing you would do is you would have multiple different values of capacitors. I do this when I design headphone amplifiers. I'll have like a 1500 bulk, 1500 microfarad. There we go. Like a 1500 microfarad bulk capacitor, and then I'll have like a 100 microfarad and a 10 microfarad and a 1 and a 0.1, and they get smaller, and you're just going down by an order of magnitude on each one, but each one resonates at a different point. And when you look at the ESR graph, the effective series resistance graph of all of those in parallel, the whole thing ends up being lower and flatter. Whereas if you have a whole bunch of the same capacitor in parallel, they're going to resonate and they're going to have a dip at a very specific frequency. And if you just have those capacitors at that one place, your lowest ESR at that frequency will be super duper ooper schmooper low, but the rest of the graph will still be pretty high. And so by putting multiple values in parallel, you're getting the benefit of multiple different dips in the ESR in each of those. And so you ultimately end up with a better performing filter capacitor, even though you might have fewer overall microfarads in filtering. So that's kind of what we're doing here with the analog. So we have a 10 nanofarad, which is a 0.01 microfarad, and a 1 microfarad. And we have that on both the VDD-A line going into the analog section of the chip, as well as the voltage reference, which is used for A to D conversion. We are not using the analog section of this device, so I'm kind of debating whether I want to bother with these. I'm probably going to go ahead and put them on the board, and I just may or may not populate them with anything other than some simple stuff. That way, if somebody wants to take the board and use it to hack some analog stuff later, they can. All the stuff will be there to have a clean power supply. For what we're doing, it's probably overkill, but that's okay. But yeah, here's the nodes. The 4.7 microfarad capacitor up here on this one must be connected to VDD3. So I'm not entirely sure why VDD3 has a separate requirement for more capacitance, a 4.7 microfarads as opposed to a 0.1 microfarads. But VDD3 does something with more capacitance. I don't know exactly why. Although that makes it look like, because it's 1, 2, 3, 4, 5, so 5.1s on all 5 of the power supply lines for the bigger chips, plus a 4.7 microfarad on VDD3. So VDD3 probably wants the 4.7 and the 0.1. So anyway, I'm going to be adding those caps. And then the ceramic filters, or the ceramic resonators, or the oscillators, we're going to be adding those too. So we've got the 8 megahertz oscillator that's needed on the OSC in and OSC out pins. We're not going to be adding this external resistor, I don't think. Value depends on the crystal characteristics. I don't think we need that. Famous last words, right? But I'm going to use a crystal oscillator. Let's see here, not that one, that one. This is the crystal oscillator that I'm going to be using. It is, if you notice here, it's got the crystal in it and the filter caps, or the load caps, built into a single component. Resonator with integrated capacitors. That's what we're building here. So one pin is going to be ground and the other 2 pins just go into there. So that's what I'm going to be using for the 8 megahertz signal source. I did not find a 32.768 kilohertz version of that for, at least not on Mauser. They may exist, but these little tiny crystal oscillators here are ubiquitous. You can find them anywhere. They are all over the place. The hardest part was finding one that had a low load capacitance. So this one specifically has a 6 picofarad load capacitance. And the reason I did that is because if you scroll down here, this section here is saying you use a high-quality ceramic capacitor in the 5 picofarad to 15 picofarad range, selected to match the requirements of the crystal. Usually the same size. The crystal manufacturer typically specifies a load capacitance, blah, 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 blah. To avoid exceeding the maximum value of CL1 and CL2, it is strongly recommended to use a resonator with a load capacitance of 7 picofarads or less. Never use a resonator with a load capacitance. Oh, that's resonator. We're not using a resonator. We're using a crystal. Okay, so maybe I can use it anyway. Anyway, sorry. I'm selecting components again. Maybe I don't need to use one that's a 6 picofarad because those are a bit more expensive. These are 25 cents each in quantity of 1. We're going to be looking at the quantity of 1,000 for what I'm doing. So that's 12.8 cents. And I don't know if you can read it there. That's 12.8 cents there. The other ones I think were 10 cents with a 12 picofarad. In any case, at this point in circuit layout, it doesn't matter. This is something I'm going to have to worry about for when I actually select a BOM and do some order some parts. As it is, there's this little tiny thing with these very two close-in lead wires that we're going to have to lay out. So that's what we're going to be doing tonight. We're going to be laying out the crystals and the power supply load caps. And then we'll see if we have any time to do anything else. But that's what I'm working on tonight. So let's go ahead and get started. There's my KiCad, and I'm going to bring up the schematic. And here we are. So a quick refresher from last time. Here's a microcontroller. Remember, we got a bunch of VDD lines and VSS lines up here. Oh, that's right, the battery. That's the other thing I'm going to do is that I do want to hook up a little coin cell spot for a battery if we intend to do that. I don't know if we're going to be doing a battery, but it's just literally, 1.8 to 3.6 volts. So like a CR2032, which is a 3-volt device, will work just fine up to the VBAT, and that will let it continue to run things like the 32 kilohertz oscillator, the real-time clock, and some other things. May or may not use it on the final device, but I'm going to go ahead and put it in on these boards. Okay, sorry, back to here. So we're going to hook up the battery. We've got some power lines that we're going to do. And then we need to hook up like the PD0, PD1, and the PC14 and 15 to the crystals. So let me go ahead and see which here. Nope, wrong one. Let's do power first. Okay. So the power, I don't need to worry about which pins they go to because all the VDD pins are going to VDD and all the VSS pins are going to ground, including the analog. The VDD-A goes to VDD and the VDD-S goes to ground. And the reference, we don't have a ref minus, that's for a bigger package, but the VREF plus, I'm not even sure we have this, to be honest. I don't remember that. But that one goes to these capacitors here. So basically, but all of these filter capacitors just go between VDD and ground. So I'm just going to make a separate section on the schematic that has VDD and ground and a whole crap ton of capacitors. Do we have a V reference? Doesn't look like we do. That actually kind of surprises me. Are any of these labeled V reference? Doesn't look like they are. So maybe we don't have an analog reference. I've got VSSA, VDDA. I got PA0 wake up. I'm not entirely sure what that is. We got a reset. Got a tamper and an RTC. I don't know what that is, but that's not it. It does not look like we have an analog reference pin on this package. So I am not going to worry about the analog reference stuff. We're just going to do these here. I notice I got a few watchers now, which is kind of cool. Thank you, everybody, for checking me out. Feel free to chat with me in the chat room. I do keep an eye on it every once in a while, and I would love to answer questions and take feedback. And if you've got anything you want to say, or if you see something I'm doing something wrong, or whatever, just reach out. Okay, so I'm going to copy that over to here. I'm going to copy that one over to here. So when I laid out this board, I laid it out stupidly because I put the VSS on top of the VDDs. So VSS stands for voltage at the source of a FET, and the VDD stands for voltage at a drain of a FET. So it's source and drain, which basically means that this is CMOS technology. There's also VCC and VEE. VCC being collector and VEE being emitter. So if you're doing bipolar, what is it? Bijunction, bipolar, whatever. The BJTs. if you're doing other technologies of transistors, then it's VCC and VEE. Really, it's the same thing. VSS, the source, and the VEE, the emitter, are all ground, right? And then VCC and VDD are your positive voltage rail. They're just different names for the same things. So that's why I'm connecting VCC here to VDD here. Just different names for the same thing. Okay, so the next thing I'm going to do is I am going to give myself a little bit more room, and let's lay out some capacitors. Device, C small. Yoink. Okay, I'm going to have to move that up, move that down. Okay, value, let's set a 0.1 microfarad on that. And, oops, nope, that's not what I wanted. Hey, knock it off. Let's look at this over here. So I just need 4 of those and then a 4.7. Okay, so copy, 8. Knock it off. Copy. Oops. I copied one right on top of itself. And then, so that's going to be the 4.7. So 4.7. Hey, come on. Can you type? And then let's just tie all these together. And then the critical thing is going to be in where we place these when it comes time to lay out the circuit board. That's going to be the important part. Dang it, that's not what I wanted. That's what I wanted. Okay, so we got 4 of those. Well, actually, I guess technically we got 3 of those and then 1 of those. But that wants that to be, okay. 10 nanofarad, so 0.01, and then another 1. Okay. So I'm actually going to take that one, and I'm going to change the value to 0.01, and then copy that over to there, value, make that a 1 microfarad. Well, let's do it this way. So VDD 1, 2, 3, and then on 3 we've also got the 4.7. And then on VDD-A, we've got the 0.01 microfarad and the 1 microfarad. Okay, so we've got all the power supply caps we need because we do not have voltage references. So I don't need that. Okay. Now let's go take a look at this. That's the power. Let's hook up a battery. Hey, Brian, how you doing? VBAT. Hey. VBAT. Yeah, we'll do it that way. That's fine. Oh, no. There we go. Okay, so I'm going to need to throw a battery on here somewhere. Hey, look, a battery. Ignoring the fact that it's not a battery, it's a cell because it's only got 1. Oh, actually, no, it might actually be a battery. They're 3 volts, the CR2032s. They're 3 volts. They're lithiums. They're 1.5 each. That is a battery. Batteries have multiple cells. So a 9-volt battery is a battery, but a AAA is a cell, not a battery. Okay, so edit. We'll make that CR2032. Okay. And then I'm going to copy my ground. And then we'll put that there, VBAT. Battery's in. Oops, dang it. Why do I keep doing that? Knock it off. Okay. So I got the battery in, I've got the power supply capacitors, and I've got, oops, I can't do it that way. And I've got the analog voltage capacitors. I think that's good for that. Let's go over and, oops, oscillators. 8 megahertz crystal. So osc in and osc out goes to the 8 megahertz resonators. So osc in and osc out are PD0 and PD1 as opposed to PC. Okay, so PD0 and PD1. Let's go back over there and OSC in, OSC out. Doesn't matter whether I've got the in and outs right because the capacitor is symmetric. And then 14 and 15, I believe, are the ones. 14 is OSC32 in, and 15 is OSC32 out. Okay. So 14 OSC32 in, and OSC32 out. Okay. So we've got those. Now I can drop a resonator. Ceramic resonator. Look at that. But that pinout is wrong. Why? I've used this a bajillion times. Why is that wrong? Okay. We will figure that out. I think it's because of the way the part is laid out is weird. So I'll have to fix that at some point. But OSC in... What? Oh, nope. I'm not looking for a component. I want to place that. OSC in and air, right. OSC out. OSC in, OSC out, OSC in, OSC out. Very good. And then copy a ground. There we go. Value 8 megahertz. And move the field value there. Okay. And then we need to do something similar for the 32 kilohertz oscillators, except that I don't have a resonator on that. So I'm just going to go crystal. We'll do the crystal, and then I'm going to need to throw some capacitors down as well. See small. Hey, look. And we'll copy that over there. Move that up to there. Value 32.768 kilohertz. Value. If it's a 12, what value of load capacitor do I want on this? I'm going to do 6 puffs. No, because they need to be in series. This is where I start pulling things out of my butt. If anybody knows how this is actually supposed to work. So, from my read of this, no, that's the 8 megahertz one. Let's come down to the 32. If you choose a resonator, well, it's not a resonator. I'm doing, oh no, it's... But I'm not using a load resonator. For capacitor load 1 and capacitor load 2, it is recommended to use high-quality ceramic capacitors in the 5 puff to 15 puff range, selected to match the requirements of the crystal or resonator. CL1 and CL2 are usually the same size. The crystal manufacturer typically specifies a load capacitance, which is the series combination of CL1 and CL2. And as we all know from our electronics classes, capacitors in series decrease. If you've got 2 capacitors of the same value in series, the resultant capacitance is half of that capacitance. They are opposite from resistors. Resistors and inductors are the same. Resistors and capacitors are opposite. So if I've got two capacitors in series that are 15 puffs. The series capacitance of that will be 7.5 puffs. Plus the stray capacitance. Okay, so I don't want 22s. I'm just going to go ahead and put 10s there because I think 10 will be... I'm pulling this out of my stinky place. Again, I'm not 100% sure because usually I see things here. I usually see values on those capacitors in the like 20 to 30 puff range. So I'm not entirely sure what that means. But, you know, we're nothing if not making this crap up as we go along. And then, okay, put some more things on here. And I think I'm pointing to the right now. So OSC32 out, chunk, and go to the left, OSC in. Okay. All right. So we've got our oscillators. We've got our power. We've got our battery. You know what? I never set some of these values. Oh, value. I think this is 47. So these values. All right. A little bit of Ohm's law. All right. A little bit about Ohm's law. If you've got a voltage is a potential difference between 2 points, right? You got a positive voltage and ground. Ground is typically considered to be 0. But honestly, this could be 5 bajillion and 3.3, and this could be 5 bajillion, and it would still be a 3.3 volt difference across the two. The fact that they're 5 bajillion volts above Earth is somewhat irrelevant until you actually go to try and touch Earth. But I'm concerning myself with the difference between these 2 points, right? So I'm going to call this one 0 and this one 3.3 because this is a 3.3 volt device. Diodes, sorry, let me stick to Ohm's law. If you stick a resistor across there, that is some number of ohms. How much current flows through that device, through that resistor, is defined by Ohm's law. Ohm's law is volts equals current times resistance. So if I've got a 3.3 volt device and I've got, let's say, a 1 ohm resistor, 1 ohms across 3.3 volts, then I'm going to push 3.3 amps because 3.3 volts times, or excuse me, 3.3 volts is equal to 1 ohm times some number, right? 1 times 3.3 is 3.3. So that means if I put a 1 ohm resistor across 3.3 volts, I'm going to be pushing 3.3 amps. That's way too much for an LED. So instead, I would rather push much, much, much less than that, on the order of just a few milliamps. But with a diode, with an LED, you have a fixed voltage drop across that diode. If you're passing current through there, that voltage drop across that diode is going to be about constant. It varies a little bit with the amount of current that you go through, but not much. Consider it a 2-volt device. The exact voltage it's called the forward voltage of the diode. The exact voltage is going to depend on the diode that you choose, but they're going to be around 1.8 to 2.4, somewhere around there. I just use 2 volts as kind of a nice round number for LEDs. So if I've got a fixed 2-volt drop and a 3.3 volt power supply, that means that I'm only trying to drop 1.3 volts across my resistor. I need to stick a resistor in there that will pass the correct amount of current with a 1.3 volt drop across that resistor. So 1.3 volts, let me open up a handy dandy calculator. So 1.3 volts equals, and I want to say, let's say we want to pass 5 milliamps. Actually, I can't do it that way. So 1.3, I'm going to do volts equal V equals IR. I'm going to bring the I underneath the V so that it's R equals V over I. So that's my V, and I want to do over I of, let's see, you can actually see it. You can't see it probably because that's nice and small. All right, well, I'm using BC. I'm using a calculator. 1.3 volts over 0.005 amps is going to give me a value of 260. But that seems, okay, that's actually reasonable. But if we do over what the what the LEDs are rated at. The LEDs are rated at 20 milliamps. So if we do instead do it at 20 milliamps, that becomes a 65 ohm resistor. Why was I putting 47s on those? We did 47s on the DarkNet badge last year, and that I'm beginning to think that that's too much. So let's just go with 100 here, value. I'm just going to stick with 100 and call it done. And let me see what that would do. 1.3 divided by 100 would give me 13 milliamps. Again, right now, this is going to matter more when we actually go to select parts. I'm just putting some numbers down so that we know what the heck we're trying to accomplish. Pull-ups for an I2C bus. These are typically 4.7K. Value 4.7K. That is just something that is common. I'm not going to bother trying to derive that for you. You can just look it up. We got the capacitor values on there. Oh, these. These are the same as those. So I'm going to make these hundreds as well. Value 100. Again, we may actually change these at some point. Okay, so are those only the only values we have right now? Yeah. I think it is. Okay. I have not been going for very long. Hey, Nick. You guys want to hang out with me while I research something? This is not something I've been able to figure out yet. So I want this board to support battery charging. I want to have a USB port on it. USB. That's what we haven't done yet. Okay. USB. I'm going to handle the charging port later. Let's go take a look at USB. PA11 and PA12. USB data minus and USB data plus. Okay. So PA11 and PA12. Oh, haha, already got them tagged. Good. Okay, let's put a connector on here. No. I think I want that one. Again, that looks purely cosmetic. All right, I'm going with that. And we are going to rotate that so I can actually have that in a reasonable spot. Okay, so copy those. Hey, look, it's even the correct orientation. Lucky me. Now, I can go ahead and hook up this ground to USB ground. And we'll do the shield as well. Oh, hey. Okay. But I do not want to hook up that VCC to my VCC system without a voltage regulator because that is plus 5 volts. That is USB power, where the rest of this system is running at 3.3 volts. So what I'm going to do, let's just go ahead and put a regulator on here for now. Let's just keep this version simple. Regulator. Fixed adjustable, that looks right. AP1117. Okay. Power. Plus 5 volts. that is going to need some capacitance as well. So I'm going to put that there. I'm going to copy that there, copy that there, copy that over there because it's going to want some on the output next to the regulator. And then copy that guy over here. Okay, but that's going to need to be a different value. So let's do a 1 microfarad, and we'll do a 10 microfarad. Okay. That'll be good. Okay, so now I can take power from USB. I've got the USB data going into the chip, and I'm taking my USB power and I'm regulating it down to 3.3 volts and I'm putting it on my VCC. What I want to do eventually is replace this here with a smarter regulator that will actually handle charge controlling for a lithium polymer battery. Either a LiPo or a lithium iron phosphate battery. They both have similar voltage characteristics. I think both of them, I remember seeing lithium iron phosphates topping out at 4.2 volts per cell, but I was reading up on some charge controllers that made it look like they top out at 3.6 volts per cell. I'm not sure. I need to do some more research. What I want ideally is something that has a variable input on one side. We'll switch it down to the appropriate voltage needed to charge the battery with all the constant current and everything for the battery charging. And then we'll bring the battery up to full charge whenever it's plugged in, but we'll still run the load whether it's plugged in or not. If it's plugged in, it runs it off of the power source from the plug-in. If it's not plugged in, then it will run it off the battery. Ideally, there would be one chip that does all of that, and I'm pretty sure that they exist. Linear makes a lot of chips very similar to that. So I that's what I want. And so I got to go do some more research and figure out what's there, because I want to be able to use a rechargeable battery for these next year instead of the AAAs that we've been using. We just ran into a lot of problems. Nick is telling me that lithium iron phosphate is lower than LiPo. Okay, why do I remember LiPo being 4.2 volts per cell? Is that a mismemory, Nick? Can you tell me that? But in the meantime, because of the delay on YouTube, I'm going to show that to everyone. How about I go to that? Those battery clips, AAA battery clips, they work great as a way of holding batteries in. In the previous years, we used the plastic, one thing that had the plastic and the two wires that went through the board. Those had some advantages and disadvantages. One of the main disadvantages to those is that the middle battery in the pack always fell out. The ones on the side at the little plastic bits kind of curled over and held the battery in place, but the one in the middle didn't have that, and so it kept constantly falling out. Crux had the great idea of replacing them with these. The only problem with these is that they are metal straight up against the board. And if you have any sort of exposed, like an exposed via or a ground plane, or if you're soldering melted the solder mask at all or anything like that, it will short with whatever's underneath it. And I think we ran into some problems with that this year. I know there were some problems with batteries shorting out to ground, and various other things. And I'm not entirely sure whether that was a flaw in the manufacturing with the solder mask being too with the hole in the solder mask being too large, or if that was a problem with it just kind of scraping through the solder mask or whatever it is. But great idea. If I do end up using the AAA battery clips like these, I'm going to put a keep out area underneath them so that there is no chance of them shorting out with either a data line or a ground plane or anything like that. But ideally, we would have a small lithium, a LiPo battery or a lithium iron phosphate. Okay, Nick is telling me that lithium iron phosphate nominal is 3.2 volts, and a LiPo, the lithium polymer batteries, nominal is 3.7. A LiPo fully charged is 4.2. and that's fully topped off. Do you know? Can you tell me what the fully charged topped off value is, or voltage is, for a lithium iron phosphate? Do you have that handy, Nick? That would be grand. Because if it's 3.6 or less, then this chip will operate on that natively, and I don't have to do any further regulation after the battery. I can just run the battery or run the chip directly off the LiPo battery, which would be nice. All right, so let's look at what we've got. We've got the radio module. There really isn't any supporting values I need to set up in the radio module. I've got my buttons. I've got my LEDs. I've got my crystals. I got the chip. I've got my status diode. I've got my infrared diode. I've got my infrared receiver. I've got my reset switch. I've got my real-time clock battery. I've got all my power supply bypass. Got my USB connector. What else is on here? What else am I missing? Programming header. Oh, that would be good. We got a couple of LEDs up here that come on the board that are just used for status update and whatnot. Daniel is telling me that the max charge voltage for a lithium iron phosphate is 3.65 volts, according to Wikipedia. And then Nick confirmed that as well. So LiFePO lithium iron phosphate is 3.6. Okay, good. So I think what I want is a lithium iron phosphate that I can use and just... I don't know why I'm still holding that up. I think I want to use LiPo or lithium iron phosphate for these then, because they got a lot of other advantages too. I don't have to worry about piercing them and having them catch fire on people's chests. So thank you very much, chat room, for pulling up that data. So I watch Leo Laporte a lot this week in tech and whatnot. He always talks about the chat room and how powerful it is to have that there. He's like, hey, chat room, go find blah, blah, blah for me. And like 2 minutes later, it shows up in the chat room, and it's kind of awesome. So thank you guys for being my awesome chat room. That is very useful information. Okay, so I need to put a programming header on here somewhere. So there's also something that needs to be done with those boot. So the boot pin here, I don't know what it is. On these modules, it goes to a jumper, and I could run the thing without the jumper on it at all, and I don't know if the jumper is just to tie something to ground so that it tells it to go into like a bootloader or something. I just really don't know. So I need to go figure out what's up with that. Something may need to be done with the boot. The other thing I want to do is I'm kind of interested in putting a bunch of female headers between... or just right next to the chip, so that people can use, these jumper wires, these prototype board kind of jumper wires, and get in and get access to the chip. We did this with the AT Mega 328 based ones, based boards. We had the row of headers right next to the chip, and it just went straight across to each one, so you could get at each of the pins on the chip very easily. Now this chip is obviously the little 48 pin tiny chip like that, so putting up headers around that is going to be a little bit more difficult, and it's going to be a lot bigger. It's going to take up a lot more space, well, relative to the chip anyway, and there are 48 of them, so that's a lot more pins that you need to expose. So I don't know what I'm going to do about that, but we'll figure something out there. Programming headers. Already got the reset switch. Got the USB connector. So programming headers and boot. I'm going to have to do a little bit of research on these, I think. Well, you guys don't mind research. No, you're getting into timing. That's not what I want. Zip, up to the top. ST-Link. Timer link. Nope, none of these are ST-Link. I know this is terribly exciting video, isn't it? I'm sorry. Oh, that's the clock tree. There's a block diagram of the entire chip. These are pretty neat. There's some I/O. Mossy Mouse F. Power supply. Yeah, see. Oh, there it is. SW clock and SWDIO. That's right. That's what I'm looking for. SWDIO. So where is that? Serial wire JTAG debug port. Interface embedded in combined JTAG and serial wire debugging port that enables and blah 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 blah. Pins respectively, and a specific sequence on the TMS pin is used to switch between JTAG, DPE. Okay, you gonna show me where those are? PA13. I'm kind of surprised it's not contiguous with it. Oh, it is. PA14, PA13 and PA14. Okay. So what am I using PA13 and 14 for? I'm not. Sweet. Okay. So PA13, I want that to be right facing. PA13 is what? SWCLK, was it? And PA14 is SWDIO, or is it the other way around? 14 is clock. And I got it backwards. Okay, well, we can do that. Exploding Lemur says, we're like a Google API, or we're like a Google AI, but not artificial. And the intelligence part can be contested too. Oh, you guys are intelligent. I love you guys. You know that. Well, you may not know that, but you should know that because it's true. All right. In the interest of keeping with standard pinouts, I don't know if you can see it, but underneath those 4 pins right there, those 4, no, my camera's not going to focus. Focus. That's what I'm talking about. She said focus. Anyway, name that movie. Anyone? Anyone? You're right. Mallrats. Good job. Okay, so this is D clock and DIO, and then 3 on one side and ground on the other. You're going to have to take my word for it. I'm going to hook up a 4-pin connector in here somewhere. We'll go up here. No, I don't know. Doesn't really matter, but con 1x4. Yoink. And let's see here. What was the pin out on this again? Okay, so 3.3. Oops. Desktop with me. Let's make it so you guys can actually see what's going on. So 3.3 volts down there. We're going to put a ground down there. And next to ground is the clock, and next to power is the digital I/O. So and copy those. Next to ground is the clock. Hey, I got it right. So in order it goes ground, clock, I/O, and 3.3. Ground, clock, I/O, and 3.3. Okay, there's my programming header. ST link. We'll go with that. Okay, so we got the programming header. What else? I got to know what to do with those boot pins. Let's go research those boot pins. Boot 0. Boot 0. That's my maximum thing. Boot modes. That's off to a good start, probably. At startup, the boot pins are used to select one of 3 boot options. Boot from user flash, boot from system memory, and boot from embedded SRAM. The bootloader is located in system memory. It is used to reprogram the flash memory by using USART1. For further details, refer to AN blah blah, that one, okay. So how do I... So there's a boot 1 pin as well. We should pay attention to that. And we have wrapped, haven't we? Well, that's unfortunate. Doesn't tell you how to actually do that. For further details, refer to AN2606. st.com. Ooh, you would like that, wouldn't you? Stop moving around. Bootloader is loaded in the internal raw memory. Is programmed. Download the application program. Communications program. Blah blah blah. Okay, that's all fine and dandy. Oi. Give me a bloody hardware. F1 XL density 10 devices bootloader. STM32F10 blah blah blah, and we are 103. So I think we qualify for that blah blah blah. STM32F10 blah 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 bootloader is activated by applying pattern 1 described in table 2 bootloader activation patterns. The following table shows the hardware resources used by the bootloader. The independent watchdog USART1 TX and RX pin. So where is USART1? Give me back to my pinouts. There, nope, that's the 64. There we are. One more. So, oh crap, that doesn't tell me which one UART1 is. USART1. Show me. PA8 and 8. That's clock. So 9 and 10. A9 and A10 are the UART1s. A9 and 10, and those are being used for keyboard. Those are the keyboard Ys, which means if you're not pushing any buttons, they are still available, so they can be shared. Huh, okay. I think the single wire can work too. I am mostly pulling this out of my ass. Okay. What I think I need is that. Bootloader activation patterns. So there are only those two pins, boot 0 and boot 1, and I just basically need to be able to tie them high or low. Okay, so boot 0 and boot 1 are what? Boot 1 is also B2. So what is PA or PB2? Wow. PB2 is not being used. Okay. Boot 1. Make that a left facing chunk, and I'll bet you that's boot 0. Boot 0. Okay. So let's get me some jumpers. Yeah. Except that I'm going to do it that way. And I'm going to copy it and flip that over the y-axis and do that. Okay. Value boot 0 or boot 0. Value boot 1. And then, as we do everywhere, we copy from a recently deployed power supply section. And then, oops. Oop. And then, right turn, boot 0, shunk, and left, boot 1. Okay. All right, so there's my boot controller jumpers. So, hey, there's that 2x3 jumper right there is used for selecting the booter. I've got the programmer header right here. Got the crystals, got the CPU, I've got the reset switch, got the USB connector, got a bunch of capacitors on the bottom side. What else do I need to recreate on this thing? What do you think? Anything I'm missing? I'm going to deal with battery power later. For right now, I'm just going to stick with what I've got with just a standard 1117 being run off of USB power. I think that's it. At least for now. This is definitely enough to get us going on a board. Debating whether I want to get that started tonight or whether I want to do that in a different episode. I think I'm going to keep these shorter than I have in the past. In the past, I've just gone like 3 hours straight through, and I can't imagine why anybody would want to watch me for 3 hours. But, hey, I peaked out at 8 viewers. I'm doing awesome. I'm like internet famous. I am probably one of the more famous people who do circuit design on the internet. That is probably true. Live streaming circuit analysis. All right. I'm going to hang out here for a little bit, and chat room, let me know if you want me to keep going or if you think I should stop now. I don't know why I'm asking you that, but if any of you guys particularly want me to keep going, or if you have any questions, or if you want me to go into some more detail on any of the part of this circuit diagram that I've done, right? You know, we've got all of the things hooked up to the chip. We've got a few extra pins that we're not using yet. I got my bypass caps. I got my status LED. I've got my infrared LED. I've got the infrared receiver. Got a reset switch. Got a battery for the real-time clock. I've got the I2C going to the OLED display. I've got the SPI going to the radio module. I've got my T9 keyboard. I've got my 32 kilohertz oscillator for real-time clock. I've got my 8 megahertz system clock oscillator. Oh, I don't know why I zoomed in. That was not intentional. I've got my field of LEDs for the backlights for the Enigma style display. I've got the programming header. I've got the boot jumpers. Got a USB connector and power supply. I think that's it. I'm going to call it a night. I will be back later, some other time. I don't know exactly when I'll be doing it. But the next thing I'm going to do is I'm going to start laying out a circuit board. The goal for this board is not to be a badge. I'm not going to be trying to lay this out as as something that's pretty or something that's aesthetic. I am trying to make sure that my circuit is correct. So I'm going to lay out the components that need to be surface mount as surface mount. Everything else that can be through hole, I'm going to try and make through hole, because my goal is to make this as solderable by beginners as possible. Now, it's an awful lot of stuff. So yeah, it is an awful lot of stuff. I don't know how we're going to handle that, or whether we just let it be an awful lot of stuff. I don't know. But I want it to be simple. I want it to be something that somebody can quickly assemble. So we might opt to swap out some of the through-hole things for surface mount alternatives and have them pre-populated. So the goal is to have a board that has the things that are surface mount are going to be pre-populated, and we're just going to leave a smattering of through-hole components for people to learn how to solder on. I want to have enough things, and I want to have enough different types of things. I want to have enough variants of things for it to be a good experience, for you to learn about LEDs and things that are polarized, that have to go in one way or the other, but a lot of other components aren't. Some that are 2 pins, some that are 3 pins, some that are axial, some that are radial, right? I just want to have some that are chips. I just want to have a good smattering of different types of things to solder in. That's something that we had really good in previous badges that this year's badge didn't really have, and I want to bring that back. But if it gets to be too much of stuff, then we may... if it gets to be too much stuff, then we may pre-populate more of it. Since I'm already going to have to run it through a fab process, putting a few more components on there isn't going to matter. So, for example, well, these LEDs are all surface mount, but they're going to be mounted on the bottom, so that's going to be harder to do. But like maybe we'll put these buttons, we'll make these switches, instead of through-hole switches, we'll make them surface mount switches, and we will pre-populate all of them. That's one option. Maybe the crystal stuff, although crystals are slightly different, and I want to give people the opportunity to do that. So, yeah, I don't know exactly what I'm going to do, but we'll figure that out as we lay out the board. My goal for this rev of the board is to just confirm that this circuit is correct, that I have correctly recreated everything on that board, and that this board that I'm building will correctly run this year's software, so that we know that whatever circuit it is that we're building is backward compatible with this year's badge. That next year's badge will be backward compatible with this year's badge, and then we can iterate on it and we can make some changes and improve things as we need. But that's really kind of my goal for the first round, or for the first rev of this board that I'm making. So that's it. That's what I've got going. If you have any questions or feedback or anything, go ahead and hit me up on Twitter. I'm at Smitty Halibut, SmittyHalibut. Maybe on one of these episodes I'll talk about where the name halibut comes from. No, it's not because I like fish. I mean, I like fish in tanks, but I don't like eating fish. It's completely unrelated to that. But yeah, so I'm Smitty Halibut on Twitter. I'm Smitty Halibut on YouTube, as you probably figured out. I'm not going to be one of those people that pimps their YouTube channel and says, subscribe to me, because I honestly have no idea why anybody would watch these videos, to be perfectly frank with you, but people are, so I'll do them. I enjoy doing them. I enjoy working on this stuff. I enjoy talking about it while I'm doing it. I enjoy having the chat room while I'm doing it, so please join us live. Watch for me. I usually announce these live broadcasts on Twitter right before I'm going to do them. Unfortunately, it's not a regularly scheduled thing, because I don't have a regular schedule. I just kind of, after I put my daughter to bed, I sit down and I'm going to go work on some circuit stuff and start up the stream. So, yeah, thanks for watching. I'll catch up with me on Twitter or down here in the comments, and we'll see you next time. Thank you so much. Be good humans.